Hello students, now we'll be solving memory-based questions of GATE 20. For more video solutions on GATE 20, subscribe to our channel and don't forget to click the bell icon for instant notification.
Hello students, welcome to the GATE Academy. We are proud to announce that we are the first institute to provide solutions to all the memory-based questions of GATE 2020. So in this particular session, this is just the continuation of the live session which I've gave you, in which I have gave you some solutions of today's electrical engineering, electrical machines paper, right? So we have solved some 5 questions there, out of which so total number of questions in today's paper from electrical machines is 7, right? 3 2-mark questions and 4 1-mark questions. So 2 other questions were still left. So let us discuss the remaining questions in this particular session, right? So this is just the continuation of the previous one. So the first question among the questions which we are going to discuss now is the 3 windings A, B and C all having 20 turns each is shown with the core, and its winding configurations are to just indicate the sense of the winding but not to indicate the number of turns, right? The number of turns in the winding X is 2. The RMS value of open circuit voltage induced in the winding X is dash volts, right? So basically the question is like this. See, this kind of configuration, the winding senses are indicated, right? So the number of turns in winding A is equal to number of turns in winding B is equal to number of turns in winding C is equal to 20 turns, right? Number of turns in winding X is equal to 2 turns, right? So basically these voltages are applied and this is the connection configuration, and what is asked is you just have to find out the RMS value of voltage induced in this particular winding, right? So this number of turns should not be counted from this figure, right? Figure is just to indicate the sense of the winding, right? How the winding is enclosed, right? So why the sense of winding is important? Because depending on the sense of winding, the flux is going to be established, right? See, 120 at an angle 0 degrees is applied across this particular winding, right? So this is the positive terminal of voltage. So what will happen? Out of the positive terminal of voltage, you will see a current IA, current through the winding A is IA, right? So because of this particular current, so use right hand curls rule, right? So we can extend right hand curls rule to this particular system also, right? I mean, to get the value of flux in a transformer core or any particular core, right? So just extend the right hand curls rule, right? So let us say this is the core and the current is entering through this in this manner. This is curled in this way. Therefore, the direction of flux is downwards, right? So flux because of A is downwards. Flux because of current through winding A is downwards. This is phi suffix A. Flux because of winding B. See, this is curling in this manner. Therefore, upwards is the direction of flux phi B. And this is phi C. Right? So if at all phi A, phi B and phi C, all the 3 are in same direction, you can represent the phasors in this manner. Right? So phi A, I am writing phi A as a phasor. Phi A is equal to phi M at an angle 0 degrees. So these phases must be different, but the concept is same. What is the concept? It says the phase displacement between all the 3 phases will be like this, 120 degrees each, right? So after this you will get phi B is equal to phi M at an angle minus 120 degrees, right? So iske baad kya aayega? The next one is phi C, which is equal to phi M at an angle minus 240 degrees, right? So 120 degrees each will be the phase difference between all the 3. Right? This is the configuration. So, see, when all the 3 phases are along the same direction, you can consider this particular phasor diagram. But whereas you can see phi A is reverse, phi A is opposite to that of phi B and phi C, right? So in this particular core. So if you have to add all the 3 phasors, you have to reverse phi A, right? So this is not phi A exactly, but what is phi A? This is nothing but this is simply minus phi A. This is minus phi a. Actual phi a is reverse of this, right? Actual phi a is just reverse of this. So I am writing actual phi a here. This is actual phi a. Phi a is equal to phi m at an angle 180 degrees. You can write it like this, right? Now all these three fluxes are added, right? So how to add all these three fluxes? Just obtain the phasor sum of these two, right? So add the resultant with this, or else obtain the phasor sum of these two, add the resultant with this, or else obtain the phasor sum of these two, add the resultant with this, right? So I can simply sense, right, that the phasor sum of these two is going to be in alignment with this particular phase phi a. So what I'll do is I'll obtain the phasor sum of these two and I'll simply add this, right? So algebraic sum is directly equal to the linear sum, right? So what I'll do is I'll find out the resultant of these two particular phases. Resultant of these two particular phases, which means the length of this also needs to be this much, right? This is the actual length of phi a, right? So if you find out the resultant of these two, how will you get the resultant of these two? One is phi m at an angle minus 120 degrees, one is phi m at an angle 240 degrees. Angle between both of them is 120 degrees, right? Therefore, resultant of these two phi r is given by parallelogram law of vectors, that is phi m square plus phi m square plus 2 phi 1 phi 2, that is phi b and phi c, that is phi m square. Cos of angle between them is 120 degrees. So cos 120 is minus 1 by 2. This cancels this, 1 minus 1 by 2. This is minus 1 by 2. Therefore, this 2 cancels this 2. You will be left with phi m. Resultant is also phi m. Magnitude of the resultant is phi m. How is the resultant aligned? The resultant is aligned with this phi a directly. This is phi r, right? Therefore, total flux is summation of these two fluxes. Therefore, phi t, let us say, is summation of these two fluxes. Maximum value, peak value of phi t is equal to maximum value of this plus maximum value of this. Therefore, phi m into 2, that is equal to 2 phi m. This is the resultant flux, which means this resultant flux, the total flux phi t, is passing through this particular winding, right? So that is passing through the center of this particular winding. So according to this flux, a voltage will be induced in this particular winding, right? So in order to calculate the voltage across this, we have to do certain simplifications, right? So this phi t, if we have some phi t amount of flux passing through this, and this is peak value, right? Induced EMF Ex, let us say Ex, peak value of induced EMF Ex maximum is given by root 2 pi f phi n. So instead of writing root 2 pi, you can write it as 4.44 pi also, right? Generally it is written as 4.44 pi, but root 2 pi will give you more accurate results, and that is the reason why I generally practice writing root 2 pi. And in this case, writing root 2 pi will simplify your calculation a lot, right? Root 2 pi f phi n. What is n in this winding? N in this winding is 2. Nx, let us say. So I'll write this in the next step, that is root 2 pi f phi n is 2. This is equal to how much? This is equal to, see, this is phi max, and phi max is, I should write phi total max, right? Just a play of representation, phi total max. So phi total max is equal to 2 times of phi max you have derived, 2 times of phi max. Therefore this is equal to 2 root 2 pi f 2 times of phi m into 2, right? You can write it as 4 root 2 pi f phi m. So if you can find out the value of pi fm, you can find out the peak value of Ex, right? You can find out the maximum value of Ex. Once you find out the maximum value of Ex, just divide it by root 2, you'll get the value of RMS, value of Ex in RMS value, right? So, to calculate this pi fm, I'll use the EMF induced in other windings, right? Hence, no losses are mentioned in this. Since no losses are mentioned in this, right? I can consider the applied voltage is appearing across the induced voltage, right? Applied voltage is being the induced voltage, right? Therefore, induced voltage in phase A, EA maximum is equal to, right? EA maximum is equal to, see here the RMS values are given. Since RMS is asked, you can simply say RMS values are given here, right? So, EA max is equal to root 2 pi f phi max. See, in one particular phase, in any particular phase, phi m is the flux. In any particular phase, phi m is the flux, right? So, root 2 pi f phi m, and n value is Na, that is equal to, Na is 20, this is phi m, right? 20 root 2 f phi m n, yes, 20 root 2 pi times of fm, right? This is EA max. Therefore, EA max is equal to how much? Maximum value, peak value, RMS multiplied by root 2, right? That is equal to, sorry, this is given as 230. By mistake, I have written it as 120. This is 230 volts, 230 volts, 230 volts everywhere. By mistake, I have written as 120, right? So it is 230 RMS multiplied by root 2. Peak value. Peak value is what I am comparing, right? So upon this comparison, this root 2 gets cancelled, right? So I will be left with pi fm, pi f phi m is equal to 230 divided by 20. 230 divided by 20, right? So from this particular thing, I got the value of pi fm. So substitute this pi fm in this relation, right? So this is equal to 4 root 2 into 230 by 20. 4, this cancels this by 5. So you got 5 cancels 230 by 46 times. Therefore this is 46 root 2. 46 root 2. What is 46 root 2? 46 root 2 is peak value. Ex maximum. Ex maximum. But what is asked in the question? RMS value is asked in the question, right? Therefore, see, you have Ex maximum induced EMF in this, peak value of induced EMF in this is 46 root 2 volts. Therefore, RMS EXRMS is equal to 46 root 2 divided by root 2, right? So RMS value is Vm by pi, right? So this Vm by root 2. This is equal to 46 volts. So what is the answer? The answer is simply 46 volts, right? So if you know how to obtain the direction of flux with this sense, right? So the key for this question lies in this particular thing. So if you have a good knowledge of phasors, you can easily calculate this particular answer, right? So the answer is finally 46 volts. So let us look at another question, right? We'll be solving the second question now. So the data for this particular question you can see on the board, right? So the question is like this: a 250 volts DC shunt motor with armature resistance of 0.2 ohms and a field resistance of 100 ohms. It draws a DC shunt motor of armature resistance 2 ohms, 0.2 ohms and field resistance 100 ohms, draws a no load current of 5 amperes. Draws a no load current of 5 amperes. I0 is equal to 5 amperes. And runs at a speed of 1200 rpm, right? So at no load it runs at 1200 rpm and draws a load current of IL is equal to 50 amperes, right? When the machine is loaded, it draws a current of 50 amperes. If the flux per pole is decreased by 5% because of armature reaction, Because of armature reaction, if the flux per pole is decreased by 5%, right, the brush drop is assumed to be 1 volt per brush, right? Brush drop is 1 volt per brush. At all operating conditions, the speed of motor under this load condition is closest to, right? The question is speed of the motor at this load condition is closest to, right? So let us construct a DC motors diagram. See, this is how your DC motor is going to be, right? A shunt field, and in parallel with this you will have RA, armature resistance. In series with the armature resistance you have the rotor circuit like this, the motor. Right? So 250 volts is the rated voltage. 250 volts DC is the rated DC voltage. Right? So the value of armature resistance is given to be 0.2 ohms and this resistance is 100 ohms. So when 250 volts is applied, the current through this particular shunt branch is always 2.5, 250 divided by 100, 2.5 amperes. Right? I'm writing the no load currents with blue and I'm writing the full load currents or else load currents. Right? It is not mentioned that this is full load. This other load conditions I'll be writing with red. Right? So if 2.5 amperes is the current through this, total no load current is 5 amperes, the remaining current will flow through this armature circuit, yes or no? Therefore, remaining current, how much is the remaining current? That is 0.5 amperes. 0.5 amperes is the remaining current. Sorry, 0.25 amperes is the remaining current. 0.25 amperes. Right? So this is the no load condition. And in no load condition, what is happening? The machine is rotating at 1200 rpm. No load speed of the machine is 1200 rpm. Right? So फटाफट EB1 calculate कर दो इस condition के लिए EB1, which means the back EMF for this no load condition just will calculate. Right? This is EB1. So EB1 is equal to how much? EB1 is simply 250 volts minus, see the applied voltage is 250 volts, 250 volts minus armature resistance multiplied by armature current 0.2 multiplied by 0.25 amperes minus 2 into brush drop is 1 volt. Right? So 250 minus 0.2 into 0.25 minus 2 into 1 ampere. So 1 volt. This is going to give you 247.5 volts. 247.5 volts. Next, you have to calculate EB2. In order to calculate EB2, you have to know the currents passing through the armature under load condition. Right? So what are the currents? The load current is 50 amperes. When a load current of 50 amperes is flowing, 2.5 amperes still flows through this branch. And through this particular branch, 50 minus 2.5, it is 47.5 amperes. 47.5 amperes is the current through this armature circuit under loaded condition. Right? Now you have to find out another induced EMF, that is EB2. Right? To find out EB2, you have to use the similar relation only. EB2 is 250 minus 0.2 armature resistance multiplied by the armature current 47.5 minus 2 into, see, we have two brushes. This is one brush, let us say. This is one more brush. At each brush, 1 volt is the drop. Right? Therefore, the total drop is 2 into 1 volt. That is the reason why I am writing it as 2 into 1. Right? This value, you are getting it as 238.5 volts. So in the question itself, it is mentioned that because of armature reaction, whenever a current flows through, heavy currents flow through the armature, what happens? Armature reaction prevails, right? Because of armature reaction, some demagnetizing effect is taking place, right? Because of which the flux is decreased by 5% of the previous value, right? So new value of flux is 100% of old flux minus 5%, right? That is 1 minus 0.005 into 5 old, right? Phi new, or else you can say phi 2. phi 2 is equal to 0.95 times of phi 1. And you have to find out the speed. Speed is, you have several other relations. See, EB is proportional to n phi. EB is proportional to n phi. That implies speed is proportional to EB by phi. Therefore, n2 by n1, I want n2, right? That is the reason why I am taking n2 on top. n2 by n1 is equal to EB2 by EB1 multiplied by, see, phi is in the denominator, therefore phi 1 by phi 2. Phi 1 by phi 2, how much will you get? Phi 1 by phi 2 is simply, you will get 1 by 0.95, right? See, I am writing the values also here. The value of EB2 is 238.5 volts, 238.5 volts divided by 247.5 volts multiplied by phi 1 is some phi 1 only, right? Now the second flux is modified flux, that is 0.95 phi 1. You'll write 0.95 times of phi 1 here. Phi 1 gets cancelled. So for getting N2 you have to multiply N1 with this. What is N1? N1 is nothing but the no load speed, that is 1200 RPM. Therefore N2 is equal to 1200 multiplied by 238.5 divided by 247.5 multiplied by 1 by 0.95. Right? This is the value of N2. If you just calculate, you will get N2 as 1217.22 RPM. 1217.22 RPM. Right? And we also have options for this question. I'll just mention the options here. Options are like this. Option A is 1220, option B is 1200, option C is 1000, option D is 900, right? So in the question it is mentioned that the speed of the motor under this load condition is closest to means, see, 1217 is closest to which number among these? 1220, right? So you will mark option A as the answer. The answer for this question is 1220 RPM. The actual value is 1217.22 RPM. It is closest to 1220 RPM. Right? Hope you have liked the video. So if you have any doubts, please use the comments section and drop your doubts there in the comment section, and share this video with your friends so that they can assess how many marks they are getting in GATE electrical machines of today's paper. Right? Hope you liked the video. Thank you.